In this video, we're going to go over section 2.6 from our textbook, and we're going to start with operations on functions here. So if we're given two functions f and g, then for all values of x for which both f of x and g of x are defined, then these functions here are defined as follows. So this will be the sum of our two functions. This is the notation that we'll use, and so we're just taking the sum of our functions f and g. Similarly, this is the notation used for the difference, and we're just going to take the difference of our functions. This is the notation for the product of our functions, and the quotient. So we're dividing our two functions. And of course, this is the case when g of x is not equal to 0, because we can't divide by 0. So we're going to go over several examples for these. The first one, we're given our function f of x is equal to 2x plus 1, and g of x is equal to x squared minus 2. And the first thing we want to do is find the sum of these functions. So we're just going to add these guys up and simplify if we can. So first let's just do some color coding. So we have this function here, f of x, and this one, g of x. So if we're going to take the sum of these guys, then we'll first have f of x, and then we're going to add g of x to that. All right. Doing so, we will get x squared plus 2x, and then we can simplify this plus 1 and minus 2, so we'll get minus 1. Okay? And then just writing it in this order, because remember, we want to write our variables in decreasing order of their powers. All right. And then something to note here is that we have a polynomial, so we know that the domain of this guy is going to be all real numbers. And then in interval notation, that'll be negative infinity to positive infinity. All right, so we're going to do the same thing for the difference of these functions. So we'll do 2x plus 1, and we're going to subtract our function g of x, which we have to put in parentheses here because we know that this subtraction is going to distribute to both terms in there. So we'll get 2x plus 1 minus x squared plus 2. So we'll end up with minus x squared plus 2x plus 3. And then again, we have a polynomial, so we know the domain is just going to be all real numbers. All right. Now let's look at the product of our two functions. So remember, we're just going to be multiplying our two functions, so we'll take this and multiply it by this. So f of x times g of x. All right, and so we can just FOIL this. So this term will multiply this one will go here, this one will multiply with this one, and this one will multiply with that one. So we'll get 2x times x squared, so we'll get 2x cubed. Then we'll get 2x times minus 2, so we'll get minus 4x. Then 1 times x squared, and then 1 times minus 2 squared. All right, and it looks like we can't simplify anything here, but we can write this like this here in decreasing order of the powers of our variables. So this should be 2x cubed. So we'll get 2x cubed plus x squared minus 4x minus 2. And again, we have a polynomial, so our domain is going to be all real numbers. All right, and lastly, we're looking at the quotient of these two functions. So we're going to divide f of x by g of x. And in this case, we actually can't simplify this further, so that's fine. This will be our answer. But our domain here is not going to be all real numbers, because remember, g of x can't equal 0, so we want to figure out what values will make g of x equal to 0. We'll do that by solving for x here. So we'll just get x squared is equal to 2. And so this tells us x is equal to plus or minus square root of 2. Right? So then our domain is going to be all numbers except plus or minus square root 2, because that will make our g of x 0. And we can't divide by 0, so our domain is going to be all numbers except for plus or minus square root 2. So in interval notation, that'll look like this here. All right. Now for the next example, we're going to do essentially the same thing. We're given two functions here, f of x and g of x, and we're going to do these operations on these functions, but now we're going to evaluate them at a given value for x. So what I mean is, first we'll find f of 0, because in this first one, our x value is going to be 0. So plugging 0 into our function, we'll get 0 squared minus 1. So that's negative 1. And then for g of 0, plugging it into the absolute value, just get the absolute value of 0, which is just 0. Okay. So now what we'll do, because we know that this is going to be the sum of our functions evaluated at x, and in this case x is 0, we can just add these guys together. So we'll get minus 1 plus 0, so we'll just get 0 for this guy. All right. Now for this next example, we have these same functions, but we're evaluating it at x is equal to 2 now. So we're gonna find f of 2 and then take out g of 2. So f of 2, plugging 2 into x squared minus 1. We get 2 squared, which is 4 minus 1, so we'll get 3. And then for g of 2, we'll just get the absolute value of 2, so we just get 2. And then plugging this in, we'll get 3 minus 2, which is 1. Similarly, we have our same functions here, but we want to find the product of f and g evaluated at minus 1. So we'll find each one again. So f of minus 1, we're plugging minus 1 into x squared minus 1. Right, so we get negative 1 squared, which is 1, and then minus 1, so we get 0. Then for g of minus 1, since we have the absolute value function, this is going to be positive 1. All right, and then since we're multiplying these guys, we'll get 0 times 1. We end up with just 0 for this guy. And lastly, we're going to look at the quotient of our two functions, now evaluated at 3. So f of 3 is going to be 3 squared minus 1, so we get 8. And then g of 3 is going to be absolute value 3, which is just 3. And so our answer is 8/3. All right. The next thing we want to be able to do is use a given graph here to find these functions evaluated at a specific point. So in this case, we don't have the actual equation for these functions, we just have their graphs. So again, this is going to be f of minus 2 plus g of minus 2. So we'll find each of those values using our graph here. So this parabola, this shifted parabola, is going to be our f of x, and so we want to find f of minus 2, so when our x value is negative 2. And as you can see, when our x value is negative 2, f of x is 0. And then we'll do the same thing for g of minus 2. In this case, g of x is this y is equal to x function that's shifted up. and it looks like g of minus 2 is going to be minus 1. Okay, so we're going to have 0 plus minus 1, which will be minus 1. All right. We'll do the same thing for this one. We have f of 0 minus g of 0. So again, we'll find each one using our graph here. When we have x is 0, our f of x value is going to be 4. And then when we have g of 0, here, our f of x value is going to be 1. Right, so then we get 4 minus 1, which is 3. Again, we want to find the product now of these functions evaluated at negative 4. So we'll find f of negative 4 and g of negative 4. Using our graph here, f of negative 4 is going to be positive 4. And then g of negative 4 is going to be negative 3. All right, so we're looking for the product of these guys. So we get 4 times negative 3, so we'll get negative 12. Okay, so for the last example, we're going to look at the quotient of f and g evaluated at minus 3. Okay, so looking at f of minus 3, so we have negative 3 here, that will be 1. And g of negative 3, so negative 3 here, will be negative 2. Okay. So then this quotient here will be 1 over negative 2, so we just get negative 1/2. All right. So the next thing we're going to look at is the difference quotient here. So the difference quotient is the slope of our secant line, and the secant line is defined by the line that goes through a curve at 2 points. Okay, so if we have this curve here, this y is equal to f of x here, this black secant line is going through this curve at exactly 2 points, P here and Q here. And if this point P here is evaluated at x, and then this is our output, f of x here, then this distance to this new point Q, if this is given as h here, is going to be this x value will now be x plus h, whatever that h distance is, and our output will be f of x plus h. Okay, so the purpose of the difference quotient is to calculate the slope of this secant line, but it also provides a way to approximate the rate of change of a function at a specific point. And so we'll get into that a little bit later, and you'll definitely see that if you're taking calculus. But for now, we're just going to look at this formula here. So the difference quotient of a function f is an expression of this form here, where again, we can't divide by 0. And so we'll look at an example of this. Let's say we're given this function here, f of x is equal to 2x squared minus 1, and we want to find the difference quotient. Well, the first thing we can do is kind of break this up. We have this first term, f of x plus h here, so let's find that guy. We know that this means we're just going to plug x plus h into our function wherever we see an x, so we'll get 2 times x plus h squared minus 1. Alright, x plus h squared, we're going to get x squared plus 2xh plus h squared minus 1. And then distributing this 2 to every term in our parentheses here, we'll get 2x squared plus 4xh plus 2h squared minus 1. Okay, so that's this term here, and now what we'll do is we'll plug this term into our f of x plus h, and then we'll plug our f of x into this here. So f of x plus h minus f of x all over h is going to be f of x here, or sorry, f of x plus h, and then we're taking out f of x, which we know is just 2x squared minus 1. And this is all over h. Okay. So the next thing I'll do is distribute this minus to both terms here. So we still have this here. Then we have a minus 2x squared and a plus 1. Notice that we have a 2x squared and a minus 2x squared here, so these guys will cancel. And then we have a minus 1 and a plus 1 here, so these also cancel. So we'll end up with 4xh plus 2h squared all over h. Lastly, there's an h in every term here, so we can pull that h out. We'll get 4x plus 2h here all over h. And so these guys cancel. And we found our fully simplified difference quotient, which is of that form there. All right. You can also, you can skip this step if it's easier for you and just go straight into evaluating it like this. Sometimes it's easier to just break it up into pieces though, especially if you have more complex functions. All right, let's look at another example. Let's say we're given f of x is equal to x squared, and we want to find the difference quotient, but we want to find it for given values of our x and h. So what we'll do here is just plug in those given values into our difference quotient. Okay, so we have f of x plus h, x is minus 2 and h is 2, so this means we have f of minus 2 plus 2. Then we have f of x, and x is minus 2, so we have f of minus 2, and then we're given that h is 2, so this is all over 2 here. Okay, simplifying just a little bit, we have f of minus 2 plus 2, so this is going to be f of 0, and then everything else is going to stay the same here. So at this point, it just becomes plugging in these values into our function here. So we'll get 0 squared here, minus negative 2 squared all over 2. We have negative 2 squared, which is positive 4, but we still have this minus out front, so we get minus 4 over 2, which is equal to negative 2. All right. And the last thing we'll look at in this section is composition of functions. So if we have functions f and g, then the composite function or composition of g and f is given by this here. Similarly, the composition of f and g, so if these guys were switched, would be given by this here. So essentially, we're just plugging in a function into another function. So here, if we have a function g, our function g will be evaluated at our function f. And in this case, our function f will be evaluated at our function g. So let's look at an example of this here. Say we're given f of x and g of x here, and we want to find this guy. So this is going to be the composition of f and g, which can also be written like this, which just emphasizes that we're plugging g of x into our function f of x. All right, so just how we did, or how we've been doing, if we're going to evaluate f of x at g of x, we're going to plug in our entire g of x into f of x wherever we see an x value. So this will be 3 times 3x squared minus 1 plus 2. Okay, because we have a 3x, so this entire thing gets plugged into our x. Distributing that 3, we'll get 9x squared minus 3 plus 2, so we just get 9x squared minus 1. All right, now let's look at g of f of x. So the composition of g and f. So in this case, we're evaluating our function g of x at f of x. So we're doing the opposite now. We're going to plug in f of x here wherever we see an x in this function. So this will be 3 times 3x plus 2, and this is squared because we have an x squared here, and then minus 1. All right. So we'll get 3 times, this is going to be 3x plus 2 squared, so 3x plus 2 times 3x plus 2. Doing so, we'll get 9x squared plus 12x plus 4 minus 1. Then we'll distribute this 3 to every term in here. We'll get 27x squared plus 36x plus 12, and then minus 1. So our final answer will be 27x squared plus 36x plus 11. All right, so not too bad, just making sure that you plug in the entire function wherever you see an x. We're evaluating the functions at another function. So the last example we'll look at is this function here. So in this case, we're given this composition of functions here, this h of x, and we want to find two functions f and g such that f of g of x is going to be equal to this function we're given. So we want to find these two functions such that when we plug g of x into f of x, we get this here. Notice though, right off the bat, we have these two repeated quantities here, this 2x plus 5. So this is an indication that this is going to be one of our functions, and it looks like we're plugging it into another function here. We have this power function, and then we have 3 times this guy. So if you see repeated functions like that, that is kind of an indication that our outside function, our f, will be evaluated at the inside function, whatever is being repeated. So what I mean is, if we let g of x be equal to what's going on the inside, what's being repeated, and f of x be equal to the function x squared minus 3x plus 4 here, then if we were to take the composition of these guys, so we're going to plug g of x into this guy wherever we see an x value, we get 2x plus 5 squared minus 3 times 2x plus 5 plus 4. And if you notice, this is equal to our given function h of x. So being able to look at a composition of functions like this and break it into two functions, f and g like this, does take a little bit of practice and just recognizing what these functions look like, but something to note here that there are other pairs of f and g that will also work for this. Okay, so there's not just one answer in this case. All right, so that'll be it for this video.